Okay, so today we'll be talking about search algorithms and the interaction between like search and the outputs that you see. I think this is really important, but it's not talked about very frequently in a lot of the like literature on deep learning or NLP or stuff like this. So I think it's kind of under acknowledged as an issue, and I'd like to maybe rectify that a little bit. Um, so to get started, I'm talking about the generation problem, and I say we have a model of P of y given x. How do we use it to generate, for example, a sentence or any other sequence of actions? So it could be an incremental parse tree, whatever else. And up until now, we've talked about a couple methods. We've talked about sampling, where we try to generate a random sentence according to the probability distribution, and argmax, where we try to generate a sentence with the highest probability. So the question here is which one of these should we be using? Which one of these is appropriate for our task? And this is my interpretation with prejudice, and some people might agree with me, but I would argue that they're wrong. But like, if we want the best possible single output, we have a user and we want to show them a single output. I would argue that you should be searching for the best possible single output. What your criterion is for best might differ, but I think you should be searching. If you want to observe multiple outputs according to the probability distribution, so in other words, you want to know what the model thinks. You want to know, like, okay, I have a model that can generate sentences. I'm going to sample 10 sentences from the probability distribution and look at them and see if they look reasonable. Then sampling would be the way to go there. Or you could do search and say this is the most likely one, but that doesn't give you a concept of the probabilities, shall we say. We want to generate diverse outputs so that we are not boring. So like, for example, we have a chatbot or something like that. One way we could do this is with sampling. So this would increase the variety in our output, and we would get different diverse outputs. I would argue that you could do just as well with something related to search. So if you want diversity, you can search, and you're going to be outputting multiple outputs. The first time you could search for the best output that you think is the most appropriate. The second time you could search for the best output that's not similar to the previous output that you've generated, for example. And I'm going to talk about diverse beam search methods that allow you to do things like this. So first I'm going to talk about sampling because this is easy. And I'm going to talk about sampling from the context of actually wanting to observe multiple outputs that follow the probability distribution that your model knows. And the reason why this is easy is we can use ancestral sampling, which I already talked about earlier in the class in the conditional language modeling, conditional text generation part. So in this case, we randomly generate words or actions one by one. So it looks like this. We have a while loop, and while we haven't reached the end of sentence or until we haven't reached our termination condition, we just sample a single token from this output. And we're done, basically. So this is an exact method for sampling as many outputs as we want from the distribution. And no further work is needed. So we don't need any better algorithm other than this to do sampling, because this exactly samples from the distribution. So any other algorithm that says it's doing sampling, according to some sort of method that was devised in a certain way will not actually be sampling from the distribution. It will be sampling from something else. Notably, this is sampling with replacement. So you could sample the same sentence twice or the same output twice. You could sample, hello there 500 times if you sampled from a language model. There are also methods for sampling without replacement, which I'll talk about later. But in general, this is all you would need to do to observe samples. So yeah. Okay, so that was easy. We finished half of the class. now let's go into the search part. And unfortunately, this is not as easy. So why do we search? So basically, as I said, our goal is to find the best outputs. So we could think of one search criterion or one criterion where literally we search for the best output. So what do we mean by best? We could think of this as the most accurate output. So in other words, any search problem is going to have an argmin or argmax somewhere in it. That's kind of the definition of a search problem. It might be an approximate argmin or argmax, so we aren't able to actually find this effectively, but it will have it as our goal. So let's say we wanted to search for the most accurate output, the one that has the lowest error. That would be great, right? You know, we find the best possible output that gives us low error. We'd love to do this, but unfortunately this is impossible, right? We don't know what a good output looks like, and that's why we spend all our time training models in the first place. So what we should remember is this is essentially our goal. We'd like to find outputs with good errors, but we can't do that because we don't know what like this reference Y looks like. So what we've done up until now is we can also search for the most probable output according to the model. So this is basically maximizing the probability according to the model that we have, and this could be, you know, a parametric model parameterized by theta or something like this. So this is good. You know, it seems to work reasonably well. The only problem is there's a big difference between this error here and the probability. And I've talked about this several times before. You know, this is why our model loss can continue to go down despite the fact that our error is continuing to get better. So like there's a disconnect between these two. And then finally, I'm going to talk about this in more detail later, but there's also the concept of something called Bayes risk. And basically Bayes risk is the model with the lowest expected error given our outputs. And so I talked about what risk is before. So basically risk is the expected error. The Bayes risk from the context of decoding is basically the expected error with respect to all of your other outputs that you think could be plausible, or all of the other outputs that have high probability. So don't worry about this. I'll get back to this. I'll get back to this later. But this is an important concept that we can think of. So another important concept here is the difference between search errors and model errors. And this is something that, again, I think is not super well covered in the recent literature on this topic. But basically, a search error is where the search algorithm fails to find an output that optimizes its search criterion. So whether your search criterion is finding the most probable output or finding the output with the lowest Bayes risk, it's basically when you fail at this argmax or argmin. You're not able to find the thing, your search algorithm is not able to find the thing that you're attempting to find according to the search. In contrast, the model error is the output that optimizes the search criterion, does not optimize accuracy or any other metric that you actually want to be optimizing. So basically, you're doing better at finding probable outputs, but you're doing worse at finding good outputs. So I have an example of this from one of my papers that I wrote before. And basically what we did is we made our search algorithm stronger and stronger. So we made our search algorithm, we expanded the number of hypotheses that the search algorithm could consider from one hypothesis all the way up to 1,000 hypotheses. And what you can see is the model score, unless you have a bug in your search algorithm, your model score is going to continue to go up. You're going to continue to get better log probability of the outputs. However, here we have BLUE score, which is an accuracy metric, right? And the accuracy metric can continue to go up, but sometimes it goes down. So sometimes, you know, our model score is not perfectly correlated with good output. So the fact that, you know, our model score is getting better, but our accuracy is getting worse is indicative of a model error. So this was in a statistical machine translation system that was optimized directly to minimize or to maximize this blue score. So this was a model that was directly optimized, like I talked about before, with minimum risk training or minimum error rate training to optimize this blue score. The story is a lot worse in regular neural models, where we're optimizing likelihood, which is not very well correlated with this final metric. So you're much more likely to see, the model score go up and the accuracy go down. So any questions so far? Yes.
When you optimize for blue score, you did some kind of reinforcement learning to optimize for blue score?
Yeah. So in statistical machine translation days, we use something called minimum error rate training, which basically tries to directly minimize the error. And the reason why you can do this is you're using a linear model with only a few features. But you can think of it as very close to the minimum risk training that I talked about last time, which is also equivalent to reinforcement learning. Yeah. Yes?
What is the model score?
Model score, so model score is like the log probability. So it's the log of this probability. So in this case, I was doing search to optimize this metric. And you can see that that particular metric is going up. So search is working effectively, but sometimes the accuracy is getting worse. Okay, any questions? Any other ones? Okay. So first, let's start out with searching probable outputs. So this is what we've been doing so far, or what we've talked about so far. And I've talked about a couple methods, which I'll just recap really quickly before getting into more advanced material. But the first thing you can do is greedy search. So in greedy search, it looks like the sampling algorithm, but instead of selecting randomly according to the sample every single time, you select the highest scoring one every time. So this is a very, very simple algorithm, easy to implement. However, unlike ancestral sampling, this is not exact and it causes real problems. Like it will often generate the easy words first. I have a concrete example of this later. And it will often prefer multiple common words to one rare word, for example. So I gave the example earlier in the class, just to reiterate here. If we have Pittsburgh, New York, and New Jersey, and you add the probabilities of New York and New Jersey, which both start with new, the probability of new would be 0.55, where the probability of Pittsburgh would be 0.4. So it would greedily make a mistake of generating new, and then be stuck generating York next. So beam search is a way to resolve this. So instead of picking the highest probability or score, we maintain multiple paths, where at each time step, we expand each path and choose a subset of paths from the expanded set. So it looks like this. At time step 1, we might expand 2 paths, or we might expand all 3 paths here. Then we subselect down to 2 if our beam size is 2. Then we expand more paths. So we expand these 6 paths. And then we subselect down to 2, etc. So it's just this expand, subselect, expand, subselect, expand, subselect. Okay. So within, yeah.
How important is the expand step? Like, should it be large as compared to the beam size?
So the expand step, usually what you do is you expand everything in the vocabulary. So it would be beam size times vocabulary size. And if you're doing decoding on GPU or something like that, that's actually not too ponderous because GPUs are really fast at doing these big operations. So yeah, here the vocabulary size is 3, the beam size is 2, so you'd be expanding 6 every time. Yeah, any other question? Okay. So within beam pruning, there's, beam search. I mentioned you're expanding and then subselecting. There's basically 3 different ways to subselect. So how do we select which paths to keep expanding? The most common variety is called histogram pruning. And basically, it's we keep exactly k hypotheses at each time step. So this is like, if people hear beam search, this is usually what you think about here. Another method is score threshold pruning. So this is where you keep all hypotheses where the score is within a threshold alpha of the best score S1. So in other words, this, like, for example, if you're doing log probability and you set your score threshold to 2, then basically you would keep all hypotheses that were at least 1 divided by e squared as probable is the best hypothesis. Then there's also probability mass pruning. And probability mass pruning basically keeps all hypotheses until you have an aggregate probability mass of like 0.95% of all of the expanded hypotheses, for example. So the bottom two are pretty similar. The top one is is not similar. So the top one is constant time for each time step. But the second two are not constant time. So they might expand, they might keep 100 hypotheses at some time steps and only 1 at other time steps. So they both have their advantages and disadvantages. So histogram pruning is predictable. It will never just blow up on you and have a million hypotheses. Score threshold pruning is nice if you want to save time, because some time steps might be difficult. Like if you're generating text, you might not know what ordering you should be putting the next words in, so you want to try all of them. So very often it's common to do both. Or especially if you're decoding just like one output at a time, you can do both. So you set a relatively large histogram beam, you set it to like 1,000, and then you do score threshold pruning of like 2 or something like that. And that way, most of the time you'll have a very small beam, but even when you get to the place where you have a really big beam, you're guaranteed that it will not be over 1,000. So this is a good thing. This is a good thing to do. One difficulty here is if you're doing batching, then if you batch together like multiple hypotheses at the same time, then it's a little bit difficult to prune variable sizes. So if that's the case, histogram pruning might be easier. So then the question is, what beam size should I use? Larger beam sizes will be slower. Also, they may not give the best results due to model errors. So if you're training according to maximum likelihood, this might not give you the best results. Yeah, I'll talk about that later. It's usually done empirically, where you experiment with a range. Usually, I've seen up to 5 almost always helps. And then it depends on how confusing your task is. So if it's something like machine translation, there's relatively little confusion. If there's something like dialogue response generation or free-form text generation or something like that, then very large beams, up to 1,000, can still give you better results. So it's really kind of task dependent. Okay, any questions? Okay. So there are some problems that can result from beam search that you should be aware of. One of them is through disparate search difficulty. So there's a couple examples of this. One example is where you're doing some sort of mixed mode generation. So yeah, actually, I removed this from the slide, but now I'm regretting removing it from the slide. So, yeah, actually, I'll explain this one first, and then I'll get back to the other examples. So, sometimes when you want to generate outputs, for example, if you're doing text generation, like translation or something like that, very often you'll want to cover specific content. Some of it will be easy to generate, and some of it will be hard to generate. So here's an example. Let's say we're translating from English to Japanese, and we have I saw the escarpment. or something like this. And escarpment is a low frequency word. The machine translation model doesn't know how to translate it well. So we have a whole bunch of possibilities for how to translate this. And some of them might be better than others. So basically, it's nearly certain about how to translate I. It's nearly certain about how to translate saw, but it doesn't know how to translate this here. So one problem is that this can cause the search algorithm to select the easy thing first and then the hard thing later. So what this looks like is basically if the correct answer is something like this. So here the hard word comes in the middle of the sentence. The search algorithm will very often punt on the hard word until the very end of the sentence because it gets scored lower than the easy words that you could be generating. So even though the ordering of this is wrong, the model can be biased to kind of generate these things, or just drop the content altogether. Just drop, hard content altogether. And this would result in I saw the escarpment turning into the escarpment I saw. So it's not like it's completely ungrammatical, it's just kind of wrong in context. So this is a real problem. Another example of this is in this paper. So this is for parsing, generative parsing. And when you're doing generative parsing, it's possible to generate either labels within a parse tree or words like this. So this could also be the case if you're trying to create like a sequence to tree translation model or a semantic parsing model or something like this. And the problem is basically these labels are very frequent, and they're also maybe a little bit more predictable than the words themselves. And because of this, the probability of generating these, especially these kind of like end bracket things, is very, very high. However, for the actual words in the sentence, this is low because it's kind of underspecified. And so because of this, we have this huge difference between the easiness and hardness of generating these different types of things. Because of this, the search algorithm makes mistakes, and this whole paper is proposing ways to fix this. And in the case of the mixed mode, stuff, basically what they do is they split this into two different buckets for like the beam search. One bucket is how many words have you generated. Another bucket is how many symbols have you generated, essentially. So by separating these into two different things, you can help like revert this balance, this imbalance issue. But the problem with this is this only works when you have an explicit like mixed mode problem, right? It only works when you actually know that tokens are going to be easier than others, and so that won't work in the case of something like translation. So what we do instead is we can have something called a future cost. And basically what a future cost is we don't only predict how well we've done up into the current point, but we also predict how much more cost we're going to incur until we get to the end of the sentence. So basically, to give a concrete example, this word here, we know that we're going to be able to translate easily. This word here, we know we're going to be able to translate easily. This word we know is going to be hard. So the G would represent all the cost up to the current point. The H would be the cost of all the words that we haven't generated yet, for example. And maybe you could get that by doing attention or some sort of, or looking at the attention of over the input, for example. So there's a good explanation of this with respect to statistical machine translation in a book on statistical machine translation. And there's also a paper by Lee et al., Jiwei Lee, who did something similar for neural networks. And the way it works is you have a future cost predictor based on the things that you've already generated, and you also have a sequence model And then at decoding time, you basically combine both of these together. So, so this is a good example of how you can do something like this. Yeah.
How do we get the supervision for the cost, the future cost?
So how do you get the supervision for the future costs? That's a good question. And basically what you do is you decode, and you at each time step you try to predict how much cost is going to be incurred until by the end of the decoding.
Okay. So it's based on the current model.
It's based on, yeah, on the current model. Yep. But that's actually the model that you want to be optimizing, right? You want to be optimizing search for the model you have. So this doesn't do joint training between the Q network and the, or as far as I remember, this doesn't do joint training between the Q network and the original model. It keeps the original model fixed and just trains the future cost. They call it a Q network, but it's the future cost is probably a more accurate term. Okay, yes?
What is cost in relation to the probabilities?
Oh yeah, so it would be like negative log probability or something like that. So it would be the thing, you're searching to minimize the negative log probability of the output, I guess.
Okay.
Yeah. Sorry, I'm flipping between maximizing the log probability and minimizing the negative log probability or minimizing the cost. Sorry, that's what happens when you put slides together from multiple slide decks. But yeah, basically, it's called cost here. And one of the reasons why it's called cost is for historical reasons. So this also, if people are familiar with A-star search, this is a lot like A-star search. In A-star search, you basically have a cost that you're going to be incurring by doing the search that's lower bounded at 0. A future cost is not the same as A-star search, because in A-star search you have to have this heuristic function, and the heuristic function can't be wrong, basically. It can't underestimate the cost to the end, and that gives you a perfect search algorithm. But in neural networks, there's no way to devise a so-called admissible heuristic that never makes this underestimation. So we just say it's a future cost and hope we can predict it as accurately as we possibly can. Yeah. Any other questions? Okay. Okay, so now I'd like to talk a little bit about search and interaction with problems with modeling. So better search can hurt results. I've shown you this many, many times. So like if we have a maximum likelihood trained model in the dark green here, basically we can search and get, increase our beam size. I'm sure there were no bugs in their implementation, so they are actually, the only reason why I didn't show this graph earlier is because they didn't actually plot their model score on the graph, and I think it's important to do that when you're talking about search problems. But you know, they're increasing their beam size and their you know, accuracy is going down. So obviously this indicates that your model score is not a good indicator of the output. And here in the light green, they have made a modification to the model score by normalizing it word by word, which I'm going to talk about later. And suddenly they see that they're not seeing the problems quite as badly, but still, as you make the search larger, you're getting worse results if you make it large enough. So the reason why is because we have model errors. Our probabilities are not well associated with our outputs. So how can we fix this? And I think the best answer to this, if you don't mind going through the work to do so, is to train your model so that the model score is better correlated with the model errors. Your model score is better correlated with the actual accuracy measure. And like I showed very far back in my slides, when you do this, actually the model score and the output accuracy can be pretty well correlated. Like this is not a bad correlation between the two. It's not anywhere near as bad as the thing you saw with MLE. And here I'm making my beam size up to 1,000, where an MLE trained model is just disastrous, and even the normalized MLE model is already starting to decrease. So I think this is the best thing you can do if you can do this, and I've already talked about ways you can do this. You know, reinforcement learning, minimum risk training, margin-based methods. And I've actually done this with minimum risk training for neural MT as well, and I've witnessed similar results. If you do this, it fixes your model search kind of disparity. Another thing that you can do, which is kind of not orthogonal, but related but different, is to change your decision rule to something like minimum base risk. And this can also help fix some errors, and I'll explain why. Another thing is you can heuristically modify the model score post hoc in order to make it better associated with what you actually want to be modeling, or what you actually want to be achieving, which is higher accuracy. So this is like length normalization, and there's other examples of this as well, which I'll try to cover. And another thing that you can do is hobble the search algorithm so that it makes more search errors, but it makes the kind of errors that you want it to be making. So like it makes errors that increase your accuracy. I am not a huge fan of this method, but it is convenient and a lot of people use it. So I'll try to introduce it here as well. So minimum base risk decoding, the basic concept behind this is we want outputs that look safe given all of the other high probability outputs. So we want outputs that look like, given all the other possible options that my model thinks are plausible, what could be good? So here's an example. Let's say we had a dialogue system that said, "What is your name?" Or a human that said, "What is your name?" And your dialogue system wanted to respond to this query. And the dialogue system knows my name is, or knows its name is Graham Neubig. I hope I'm not a dialogue system, but I should have thought of that before I put this example up there. But substitute that in for the name of your favorite dialogue system. However, because it was trained with maximum likelihood and it's seen lots of data where people have said, I don't know, in response to questions, and also because Graham Neubig is relatively low probability compared to other things, the highest probability thing is I don't know. The second highest, which is a little bit lower, is my name is Graham Neubig, my name is Neubig. So I don't know has a higher probability overall, but if you look at all of the similar things here, these are higher in aggregate. So the way this is operationalized is as searching for a hypothesis that minimizes the risk given all of the other hypotheses that your model outputs. So it looks like this. So here, y prime is all of the outputs that your model thinks might be plausible. These are the probabilities of those. So that would be, or like, for example, maybe it could be these 4 outputs. These are the probability of each of those. So that could be 0.3, 0.2, 0.18, 0.17. And then the error is between the, these 2 hypotheses. So the easiest way to implement this is within re-ranking. So I'll try to give a concrete example along with this. But the easiest way to implement this is through re-ranking. And what you do is you create an n-best list. And then you create an error matrix and a probability vector. So our probability vector, to go back to the previous example, our probability vector would be, let's say we just have a 4 best list. So our probability vector would be 0.3, 0.2, 0.18, 0.17. And our error matrix would be essentially the error between each of the hypotheses. So assuming that if you get it exactly right, you get an error of 0, the error down the diagonal would be 0, because every hypothesis has no error with respect to itself. And then if we look at my name is Graham Neubig, my name is Neubig, these are all very similar. So maybe my name is Graham and my name is Neubig are a little bit worse matches because they're missing a word. So between hypothesis 2 and 4, we would have an error of like 0.2 and 0.2. And then my name is Graham Neubig and my name is Graham Neubig. These are all good matches with each other, so they would get the lowest error, like 0.05 or something. And then we have I don't know, and my name is something or other. And all of these are very different, so they get a very high error. They're like 0.8. So based on this, what we do is we create these two things. We create the error matrix and the probability vector. And then we can just multiply these together to get the risk. So what this will do is this will give us another vector. So sorry, this should actually be over. But we'll get another vector, which is the like expected risk. And maybe the expected risk of P would be something close to 0.6 or something like that, because you have lots of 0.8s in there. This would be like 0.3. Then this would be like 0.2 maybe, because it's pretty safe with respect to the other two hypotheses. And then 0.3 or something. So if this was the case, you wouldn't select this I don't know, because it's way worse. It's bad with respect to all of your other plausible hypotheses. You might also not select the second one because it's a little bit worse with respect to this one. So you pick the one in the middle, which is safe, right? Because it's similar to all of the other hypotheses in that best list. Yeah.
Is it done on each time step to select, like to choose the K options, or is it done at the end?
So I'm talking specifically about re-ranking at the very end of search. You could theoretically do it at every time step. The only problem is, how do you calculate this error at every time step? And if you have something where it is easy to calculate the error at every time step, like let's say we're doing part of speech tagging or something like that, then it would make sense. But if you're doing something like language generation, then it's non-trivial to do this. Let me put it that way. It's not impossible. So if you want to be clever and come up with a way to do this, then that would be great. But it's much easier to do it in a re-ranking setup at the end of decoding. Yeah. Any other questions? Yeah.
This is under the assumption that the most common one is the best, but how does this help when you have no frequency? Like when you have a translation that's very rare, or like something like that.
So this is not necessarily the most common one. It's the one that's most similar to others.
Yeah.
So if there's only one possible output, still this is better, because even if there's only one possible correct one, okay, let me put it another way actually though. So if your error function is just whether you get the sequence 100% correct or not, if it's just like whether your error is, if the sequence is the same, you get 0 error. If the sequence is different, you get 1 error. Every single time, this matrix is going to have 0 down the diagonal and one everywhere else. And if this is the case, you'll always just pick the highest probability one. So this minimum base risk decoding only works in the case where you can say relative, like what would be the relative error of picking my name is Graham, given that the correct answer is my name is Graham Neubig. And if that's the case, then no matter what your error function is, it still would be useful. It still would be useful. And if most of the others have very high error, most of the others are like 0.95, 0.95, 0.95, then basically it will reduce to just picking the highest probability one, which is what you would do anyway, right? So, yeah.
So in an ideal case, you want to pick something high P,
Mm-hmm.
but low errors.
Yeah. Mm-hmm.
So then, if you multiply them together, then are you taking the argument or arguments?
Here you would take the argument of the expected of the risk, because you want the one with the lowest expected error.
Then you also want things with high P, right? But higher P here would increase R.
hierarchy actually would, so yeah, sorry, this is confusing because I have these in the opposite direction, but basically this 0.3 will be applied to all of these scores. So if I delete this, basically what you'll be doing is you'll be taking 0.3 and multiplying it by all of the columns, 0.2, 0.18, 0.17, sorry, I said all of the columns, all of the elements in the column. So basically, another way to look at this is taking the most probable hypothesis and upweighting it as much, with a probability of 0.3, with a weight of 0.3. It's taking the second most frequent hypothesis and weighting it with 0.2 and considering the risk from all of these. So like, let's say we had a, let's say the first hypothesis here had a 0.99 probability. If that was the case, this column would be weighted 0.99, all of the others would be weighted very low. And because we have zeros down the diagonal, that would mean that most of the probability would be on the first column where this value is 0. So this value here would be very close to 0. So in other words, like if the hypothesis itself has a very high probability, its risk will be very close to 0. We can go through the math later if it's hard to follow here, but yeah.
When you're finding out the error between these and rank normalization, it's going to be only that something like blue score, right? One minus blue score.
Yes, it could be.
So one thing is that you need to compute afterhand your rank results in order to do this, right? There is no way for you to come up with a scheme why trying to optimize this.
Well, do you mean training time or?
Yeah, I mean, training time, you have to like get these are the best results, and this like kind of post-processing which is kind of not like that.
Mm-hmm. So at training time, you can train towards risk with respect to the true answer, which we've already talked about, a couple previous times. If you really wanted to, you could probably incorporate this decoding algorithm into something like the structured perceptron algorithm. Because the structured perceptron algorithm, basically the idea is you do argmax, and then you get an output, and then you use that output. So like theoretically it would be possible to train for that, but if you wanted to incorporate a similar idea at training time, I'd just do minimum risk training like I talked about last time. Yeah. Any other questions? Yeah.
I wonder if maybe to answer this with like longer tests, you're predicting like paragraph, does this begin to break down?
Oh, okay, very, very good question. So for longer sequences like paragraphs, does this start to break down? And to ask a question back, why do you think that would happen?
I don't know, I was trying to think of a concrete example.
Mm-hmm. Yeah.
It's just because you might have like a ton of predictions if you don't limit your size of the prediction size.
Yeah. So for prediction tasks like paragraphs, it is very possible that this would break down somewhat. And the reason why is any sort of re-ranking algorithm where you expand an n-best and then you re-rank it is not necessarily a very good decoding algorithm. It's not a very good algorithm to do search, basically. And if you have to do re-ranking to do search, then it is very likely that you will fail to optimize this objective well. And you need a huge n-best list or something like this. Other than that, there's theoretically no problem with applying this to paragraphs. If you could expand your n-best list infinitely, it should work just as well there. So that, in particular, would be the place where you'd want an algorithm that can also do some sort of optimization with respect to this during search time as well. So, another option would be if you generated n-bests for each sentence independently or each coherent chunk, you could then do a sort of combinatorial optimization algorithm on top of it. Recently, I like playing with integer linear programming. So integer linear programming is a technique that you can do to solve these combinatorial optimization algorithms. And I bet you could solve a thing where you wanted to select from like a bunch of sentence level and best lists to optimize the overall like risk of the paragraph or something like that. So that would be another option. Any other questions? Okay. So that being said, I would like to talk about one thing that can help solve the diversity issues. So like one of the big problems with n-best re-ranking methods is if all of your n-bests look really similar, they're not going to be helpful. So if all of your n-bests have, and this is very common, I don't know if anybody has implemented beam search, but let's say you have a beam of 5, and you output the top 5 examples, almost always all of the variation in the output is near the end of the sentence, just because they're failing to search and they're forgetting things earlier in the sentence and dropping off all the variation in the beam. The entries in the beam can be very similar. There's improving diversity in the n-best list can help. There's a bunch of different ways to do this. One way to do this is by trying to encourage like diversity in the responses by downweighting things that have high language model probabilities. So this is particularly this was done particularly in the context of dialogue response generation, where it tends to generate boring things like I don't know. This actually isn't the best. This isn't the best example of something like this. And with respect to n-best re-ranking, a better example of this is there's a lot of work on like basically splitting each of the outputs into buckets, into like 4 buckets or something like that, and making sure each of the outputs in each of the buckets is sufficiently different from each other with respect to n-gram overlap or something like this. I realize I forgot to put that slide here, but if somebody's interested, I can upload it later. So another thing, I put it here because it kind of has to do with diversity, but there's also a really kind of algorithmically interesting paper recently on sampling without replacement. So as we know, sampling with replacement is easy in these models. It's trivial. We just sample each output one by one, and we can get outputs. But then we might get hello there 50 times in a sample of 100 in a dialogue system. So what we can do instead is there's this like stochastic beams and where to find them paper that basically turns beam search into like a sampling based process, and it has this beautiful derivation that is too large to fit in this slide, but you can go read the paper if this sounds like something of interest. Okay. So now I'm going to move away from the kind of like theoretically principled things and move more into heuristics. And there's 2 varieties of heuristics that lots of people use. The first one is heuristic modifications to model score. And a typical model error is length bias, where in many tasks, for example, MT or any other sequence generation task, the output sequences are of variable length, and maximum likelihood plus local normalization results in the probability gradually decreasing over time. So basically, every single time you're adding a log probability, log probabilities have to be negative because probabilities have to be less than or equal to 1. Or I guess not positive. So it have to be at the very most 0, usually not 0. So running beam search may then favor short sentences, which was exactly the example that I talked about before. So one very common way to fix this is to normalize by the length, dividing by y. So basically what we do is we take the log probability, and we divide by the length of the output. And basically what this is saying is I don't want to get the, I don't want to get just the, like the highest scoring output. I want to get the output that has the highest score on average for each word. So what is the probabilistic interpretation of this? There isn't any really. So like this is no longer a probabilistic model. It's basically like a scoring model. Because in a probabilistic model, we could add up the probabilities over all of the output sequences and it would add up to 1. Theoretically, the differences between them should correspond to some difference in confidence. Now we've thrown that out the window. So this is just a score. Nonetheless, as I showed you before, if you compared the dark green line and the light green line, this is a very effective way of modifying the score. So it's not as good as fixing your search algorithm. And actually, if you don't believe me on this, I have a concrete example from one of my papers. So here we built a strong system for a shared task on machine translation. And basically here, this is a maximum likelihood based model. And we had no length normalization included. And we have our blue score, our RIBE score, which are two translation evaluation metrics. This is the length ratio. So you see it's consistently generating things that are 90% of the expected length. So we added length normalization. In this case, I added a length penalty, so you got a little bit of probability every time you added a word. And this made the ratio perfect, which is great. It fixed our length problem on average and increased our blue score by a couple points. But then we did minimum risk training, which attempts to make better outputs in general. This fixed the length ratio, and it gave us on average 2 blue points, or the ensemble model got 2 blue points better overall. So it's not only fixing the length problem without doing any sort of normalization, but it's also making it a true probabilistic model. It's also improving your scores overall. So I don't want to sound like a broken record, but I kind of like people. I like when people do things kind of the correct way as opposed to the heuristic way. So this is another example. So this is heuristics where they decided that dividing by length wasn't good enough. So this is what Google's original machine translation model used. And so dividing by length wasn't good enough, so they divided by the length penalty, which was 5 plus the length to alpha, divided by 5 plus 1, not 6. I'm not sure why, but 5 plus 1. So they came up with a more complicated heuristic, which worked a little bit better. And they also added an additional heuristic that you should try to cover all of the words in the input by looking at the attention vectors. So, sure, if you're really married to maximum likelihood training, this might be a good way to fix your model, but I prefer a little bit less magic in my models. This is something that I prefer a little bit better, which is still kind of a heuristic, but not quite as much. So what they're doing here is they're basically predicting the length of the output given the length of the input based on corpus statistics. So you take a model where you calculate the length of the input. Let's say the length is 10. And based on the length being 10, then you can calculate the percentage of the time the length of the output was like 7, 8, 9, 10. Like this, and you can use that the log probability of this distribution to bias your probability. So basically, they add this length penalty together with the actual probability of the model. So this model now kind of has a probabilistic interpretation. It's more like a mixture of experts model, where you have one model just giving uniform probability to all things that are the same length, and another model, giving a uniform probability based on the conditional distribution of the length, and you have another model actually scoring. So this is maybe a little bit better. Okay. Any other questions? Okay. Yeah.
These normalization tricks doesn't work if you want to predict a smaller output. Right? If you want the correct output is actually small.
Oh, of course they do. You know, they're biasing towards longer outputs. So if your output should be short, especially for these ones, they're biasing towards longer outputs. So if your actual output is short, then you're going to be in trouble. That being said, you know, like empirically, that's usually not the problem with these models, but yeah, that is definitely the case. Any other questions? Okay. So finally, I'll go into hobbled search algorithms. What I mean by hobbled is we're basically trying to create a search algorithm that gets worse model score because the things that get poor model score are getting better accuracy. So one example of this is making your beam size smaller to improve accuracy. But how else can we modify the search algorithm? And here are a couple examples. This was from a paper by Holtzman et al. Recently, where they have a couple examples. So here they ran beam search to optimize the model probability, and got bad results on kind of an open-ended text generation task. They also did top K sampling, where they took the top 640 things in your vocabulary and kind of randomly sampled only among these. They also accumulated the top 95% of the probability and sampled among these. And basically, the result that they find is when you have a maximum likelihood trained model, the final one seems to give things that look better to humans to some extent. But I would like to give a little bit of caution about something like this. And the reason why is, number one, is sampling necessary for diversity? And the answer here is this is questionable. We could do diverse beam search instead, and we could directly, find diverse outputs that nonetheless maximize our scores. Another thing is results are inconsistent from run to run. So if you need, you would need to consider the variance in this when you're reporting results, in addition to, for example, variance due to random training seeds and data selection. And finally, I think the biggest concern about this is it conflates model and search errors. And the reason why this is a problem is if you make a better model, you might get worse results because now the search algorithm can't find the outputs your model likes, or you have hobbled the search algorithm in a way that makes it favor things from a poorer model, but your better model, you wouldn't need to do it in that way. So I think this is a really important thing to think about if you're considering these sorts of approaches. So needless to say, I would suggest one of the other alternatives that I mentioned. But these are convenient. They're easy to implement. Okay, any questions? Okay. So finally, I'm going to talk a little bit about search and training. I'm actually going to talk about this very briefly because I already talked about it 2 classes ago in the context of search-based structured prediction. But one example I gave there was beam search optimization. So I think I talked about this 2 classes ago. I'm not going to go into it in more detail, that much more detail. But basically, this is during beam search, you're upweighting the things that have fallen off your beam, and you wouldn't be able to find them anymore. So there's a kind of interesting paper by Kartik Goyal here that I'm also a co-author on, where they basically take this beam search optimization idea, and or where we take this beam search optimization idea and we turn it all continuous. So basically, you take every operation in the beam search and you turn it into a continuous function. So instead of your argmax, you're doing a peaked softmax. Instead of your nbest, you're doing a kind of soft nbest selection over the vocabulary and stuff like this. So practically, I don't think a lot of people use this because it's kind of difficult to implement. But I think it's a cool idea if you're interested in search and training together, and it might be applicable to things that you're working on. So another thing that I'm putting here, this is actually a variety of value-based reinforcement learning that I talked about before. So in value-based reinforcement learning, just to recap, we have a neural model that is an actor that predicts the next actions, and we have a critic that is predicting the final reward. And the actor is trained similarly to reinforce, where the critic is trained with, what was it again? I forget what TD stands for. Temporal difference, yeah, okay. Yeah, temporal difference. But anyway, it's trained to predict, essentially predict the rewards. So this is, the reason why I put it also here, in addition to the reinforcement learning place, is because it is quite similar to this concept of a future cost. Because basically what the critic is trying to do is trying to predict how well you're going to be doing in the future. And this Q network also is trying to predict how well you're going to be doing in the future, or at least the difference from how hard it is going to be to do the rest of the output compared to what it is now. So in Lee et al., they did not train this model, train them together, but an actor-critic style method could be something that would allow you to do that. Okay. So, oh yeah, I have equations here, but yeah, I don't think looking at big equations is the most productive thing to do. So, so are there any questions about this? That's all I have for today, so we can finish a little early. Okay, so that's all I have for today. But as I said, I think this is really important and somewhat underappreciated. The interaction between model errors, search errors, etc. So hopefully you can keep this in mind as you're going forward and implementing your projects. So, thank you.
Quick question.